Okay, thank you so much for having me here. Thank you for organizing this nice gathering, and thank you all for coming this lecture. So I will be giving lectures, 4 lectures, and today will be about some overview of what I would like to discuss throughout the week. And in particular, I'd like to give some motivation and show some phenomena and also give some insights into these things in a little bit informal way. And then I'm going to go into the details and the rigorous from tomorrow. All right. So before I start, so what I'm going to present throughout the week is based on the work with these people. So some of them are here, and in fact, like the whole thing has started because of Bert's vision on this type of things. Okay, so and also let me just emphasize one person. So Shinyu, who's sitting over there, so he's a student at Northwestern, and so the second part of this talk will be about the heavy tails in deep learning, and he has been the workhorse of that part. All right, so let me start with this notation. So deep neural network has been at the center of the AI revolution throughout the past 10 years or so. So what's particular about this is that so what's different from the traditional statistical learning is massive overparameterization. So if you're a classically trained statistician, you would have dismissed neural network because it's such a there are so many more parameters compared to the data, and but somehow you expect that this is massively overfitted and it's going to work fabulously for training data, but you wouldn't expect it to work for test data. So you learn these things, you can memorize everything, but how come it generalized to the unseen data? So the mathematically, not just neural network, but any machine learning problems would be training of machine learning algorithms would be formulated as loss optimization problem. In particular, in the deep learning setting, this loss landscape is highly non-convex. So according to Forehead, it was not even clear how one can actually optimize such complicated function. Oh, by the way, I'm referring to Forehead and Nocedal. So I think we can write perfect. So but somehow it works really well. Some optimization algorithms work really well, and in fact, sometimes people change the structure, the architecture of the neural net if they cannot optimize the loss function, and that's actually some of the main some of the essence of the advances in this AI in the recent test. So one interesting part of this is so-called algorithmic regularization. So it turns out that which numerical algorithm you use to optimize this loss function matters a lot. So no matter which optimization algorithm you use, you often are able to achieve near zero error for training data. So memorize almost all of these. But then depending on which algorithm that you have used, you may end up with different local minima, which are almost global minima because you can almost achieve near zero error with many different ways. On the other hand, the performance of the test data is very different depending on which algorithm you choose, how you get to this weights. So turns out that stochastic gradient descent and their variance are the method of choice. And in fact, there are some interesting observations. So first, when they have started using stochastic gradient descent, it was not because people expected that SGD will work fabulously on test data. It was more because of the computation reason. You cannot afford computing the actual deterministic gradient. So you just look at subsample, like a subset of the samples, and only compute the gradient with respect to these. But so given this, you expect that if you use a larger subset of data, so that you have smaller variance in terms of the smaller noise in terms of stochastic gradient, then you'd expect it, the SGD works better. And in case you can actually compute the actual gradient, you may expect even better. But it's actually the opposite. So the small batch, which means small batch stochastic gradient, means large stochastic gradient noise, works the best if you make this batch size larger so that you have smaller noise. Then the test performance is worse. And if you use deterministic gradient descent, terrible. So exactly the opposite of what you would expect if you are a classically trained optimizer. Of course, what your goal is not to optimize the loss function itself. What you want is to find something that works for the test data well. So if you really think about it, then it's not that straight, but that's just on the surface level, it might be a curious thing. Okay, so so this is how I think all of these questions have started. So you have multiple local minima, and all of them seem to be able to achieve very good training performance. Like so, work really well on the training data. So you have multiple local minima that are more or less the same for the training data, but some work better and others work worse for the test data. And so they associated with what this observation that small batch works better, large batch works worse, was so why small batch SGD is better? Because SGD seems to have this mysterious capability to find flat local minima as opposed to sharp local minima. So this one of the first people who had made this observation was Gordon Lucetta that I mentioned at the beginning. So in other words, this one tends to generalize better than these ones. So there is some debate surrounding this. So some people don't believe this, but this seems to be there seems to be some pretty convincing empirical evidences, and our numerical result experiment also suggests that it's probably right. So let's just accept this as a general principle. But let's suppose that flat minima does generalize better, sharp minima don't. Then still the mystery remains because let alone finding local minima with the right geometry, how does SGD finds SGD like explores different local minima? Because the traditional way you try analyze the behavior of SGD, global behavior of SGD, is to approximate SGD with small noise Langevin diffusion, and then think about how it behaves. So classical metastability theory predicts that it shouldn't happen. It should be it should take exponentially long amount of time for SGD to move from one local minimum to another one. So we're going to get back to this example. This is some like just one-dimensional synthetic example, but so it's easy to think about it in this way. So I'm gonna this will be a running example throughout the first lecture. So there are specific numbers attached to this, and it should take like 10 to the a few hundred iterations to move from any of these. So from here to here, or here to here, and so forth. So it should not happen, in other words, within training time horizon of any realistic machine learning algorithms. But this is because when you are approximating SGD with small noise Langevin diffusion, you're implicitly assuming that the gradient noises are lighted. So some around 2019, some interesting argument came out. So since Umut is not here, I guess, but he will be here later today. So he's one of the people who made this very interesting argument that, all right, what if the stochastic gradient descent actually, stochastic gradient noise is actually additive? So that's when I actually first learned about this problem in this generalization mystery in machine learning, because one of the co-authors, Mert, I think Mert will be also in this workshop later, probably, has visited Northwestern and gave a talk, and then he gave a talk about something else. But when we were meeting one-on-one, he told me about this, and also Bert told me about Bert's results around the same time. So I got super interested. But then what's troubling with this argument was that so this is really interesting, because what this like this just thinking about the possibility of heavy tails, that it gives you some indication that if so, then SGDs can actually escape from any local minima with a single big jump. And also there's some preference over wide local minima as opposed to sharp. So that was really interesting. But then what was not clear at that point was that when people actually use SGD, they don't use pure form of SGD. So especially when SGD seems to be jumping around, they don't allow it to move long distance in one step. So what they do is keep the direction, but then make it shorter. So it's called gradient clipping. So you're truncating essentially you're truncating the gradient noise. So if you truncate gradient noise, what's heavy tail? You go back to the light tail setup. So now the question arises: like, are you by applying this so-called gradient clipping, which by the way is very popular variant, and in many contexts we actually cannot even train with training data, cannot even include training error, let alone test error, if you don't employ gradient clipping. So so the question arises: like, is this going to cancel the heavy tails? So here's the trailer. Let's focus on this part. We're going to get back to this picture later, but these are heavy tail cases. These are light tail cases. And this is the loss landscape. So these are wide, flat wide local minima. These are sharp local minima. So you see that in light tailed SGDs, if it has no capability whatsoever to escape from any local minima that it has started. So it has started from here, so it has to stay there, just as you have expected from theory. Heavy tail cases, you see that SGD is capable of exploring all 4 local minima, but and in the pure form of SGD, it still visits the sharp local minima from time to time. On the other hand, the clipped version, truncated one, actually the sharp local minima almost disappears from its trajectory. So these are histograms of the locations that this SGD has visited. So it's actually the opposite. Instead of canceling the heavy tails, it actually reinforces the heavy tailed behavior that we have experienced. So
when you say about light tail, you are thinking about truncated light tail, the essence.
So right. So this is this one is a pure form of SGD. This is a truncated version of SGD with light tail stochastic gradient noise. So no matter what, whether it's truncated or not, it just stays there forever in the same way in the attraction field that it has started. So yeah, so it's probably going to be more clear toward the end of the. Thank you. All right, so the lectures throughout this week will be about the mathematical tools that can unravel and that helps to understand this phenomena. Also allows you to control these types of phenomena. So at the center of it, there's catastrophe principle. And I'm gonna start with reviewing what catastrophe principle is. But before that, let me give you a quick outline of the lectures that I'm gonna cover. So today will be the motivation, phenomena, and insights. And in the subsequent lectures, I'm going to be going into the details that I'm going to touch on today. All right, so the catastrophe principle. So the nominal behavior of the stochastic system is deceptively oblivious to the tail behavior of the underlying random variables. But when it comes to the rare events, there's a sharp dichotomy between heavy-tailed systems and light-tailed systems. So there are different ways to define the heavy tail. So people use different definition for when they are referring to heavy tail. Some people think of infinite variance, but what I would like to think about it is the boundary is at the exponential distribution. But so I'm going to get into this the detail later this week. But roughly speaking, there are light tail distributions and heavy tail distributions, and you probably all are very familiar with this. But the light tail distributions are the ones where you see the rare the extreme values very rarely. The heavy tail distributions, you see those extreme values much more often. So the normal distribution follows the human height distribution follows the normal distribution pretty closely, and that's why you don't see people who are like 1,000 times taller than others. So this person was the tallest person ever, and you see that compared to the other normal people next to him, he's really tall, but not as tall as twice of the average people. On the other hand, the number of Instagram, the followers of Instagram accounts, there are many Instagram accounts with 1,000 times more followers than average Instagram accounts, and even million times. Same for human wealth distribution. Like there are people who are a million times wealthier than the average Americans, for example. So that's because those degree distribution network and human wealth distribution follow law, which or regular variation as for previous principle. But that definition was recently introduced earlier today. So you can imagine that because of this difference in terms of frequency itself, there will be more rare events, system-wide rare events in heavy tail systems. But that's not all. There's actually structural difference the way the rare events arise. So roughly speaking, in light tail systems, the rare events, system-wide rare events arise because everything behaves slightly different, as if the whole system, entire system, is conspired up to drive you to the rare. On the other hand, in the heavy tail systems, the system-wide rare events arise because just small number of catastrophically catastrophic failure, let's say. So for obvious reasons, they are called catastrophe principle and conspiracy principle. I think I've seen these terminologies for the first time from Adam Weirman's presentation, but I like this dichotomy. And there, by the way, there's some interesting boundary behavior in between light and heavy tails, and Sergey knows a lot about it, and Bert also knows a lot. But the focus throughout this week will be very heavy tailed, far from the boundary case throughout this week. All right, so that might be a little bit abstract. So let me show you some concrete example. So this is a classical insurance risk model, and you start with the initial capital C. You collect premium linearly over time, and claim sizes are IID, and this can be heavy tailed or light tailed. And then the claims arrive following the toss and toss. It's a simple model, but if you feel rusty about these things, then don't worry. I'm going to show you lots of pictures. But because we cannot do much about the exact probabilities, so we would like to look at the asymptotics, and in particular, we're scaling both time and space linearly. So what this means is that we're gonna be looking at a large loss over a long time period. Okay, so these are some simulation results. So I've generated 10 simulated paths of this, and these are like heavy tail cases. And you see that it's going up and then going down, but other than that, there's not much pattern that you can recognize from here. But as the scaling parameter increases, you start to see very clear patterns. So all these paths are more or less straight and has gentle upward curve, and it's regardless of the heavy or light tail. So this is because of the law of large numbers, the functional version of law of large numbers. So the path is supposed to converge to this straight line, and if you set the premium in such a way that it's greater than the expected claim size, then you are bound to thrive. So and again, this is regardless of the tail distributions. So okay, so the nominal behavior is oblivious to the tail distribution, at least in terms of the law of large numbers. What about rare events? So let's suppose that we are interested in the event that the path, capital reserve falls below 0 between time 0 and 1. So again, we are scaling the time, so it's we are looking at actually the time between 0 and n. So because this is a nominal behavior, something like this will be a rare event. And but there are many different ways that this may happen. So this is also a possibility, and these are all possibilities. So let's see if some patterns still arise in rare cases. So these are again simulation results, but this time I discarded the cases where it didn't go bankrupt. So I've only collected the bankruptcy cases until I collect 10 of them. So this is basically same as sampling from the original distribution, even the bankruptcy. Or so again, not much pattern clear here, but as the scaling parameter increases, clear patterns emerge. But this time, very different, right? So in light tail cases, still a straight line, but the slope is different. The slope is in such a way that it hits 0 at the end of the time horizon. In the heavy tail cases, you see that almost everywhere it looks straight and also has gentle upward curve. So it looks normal almost everywhere. But there's just single point where it behaves very differently. So a huge claim arrives and drives you guys out of business. And it's always because of one huge claim. So let's look at another example. So the same event that it's below 0, but let's add this constraint that jump sizes cannot exceed D. And let's say D is less than C, so initial capital reserve. So that the light tail pattern is still the possibility, but the heavy tail pattern is no longer a possibility because you need jump size larger than D here. So let's see how it changes. The same simulation experiment. And as the scaling parameter increases, you see that light tail pattern didn't change, but the heavy tail pattern has changed. So instead of single big jump, there are exactly 2 big jumps. And again, everywhere else, it's gentle, a straight line with gentle upward curve. So these are the manifestation of conspiracy and catastrophe principle. And so let me, but this may not be the interest of machine learning workshop, but let me just take 1 minute to appreciate what this means. So if you have like this second condition that you cannot have jumps larger than D, you can think of it as claims larger than D. D is covered by Rhee. So the first case was without reinsurance contract. The second case is when you're protected with reinsurance contract. You see that the light tail pattern didn't change. So the most likely reason, or in this case, you see that it's always because of the most likely reason. So second likely reason doesn't play the role. Like it's the most likely reason, it dominates the probability. So the probability did not change. Probability of bankruptcy didn't change. The risk didn't change using by having reinsurance. On the other hand, in the heavy tail cases, you need 2 big jumps as opposed to 1 big jump, and you're going to see soon that this means that much smaller probability. So you are protected by getting reinsurance contract. So depending on whether the underlying uncertainties are heavy tail or light tail, whether you should get a large claim reinsurance contract changes. All right, so these types of dichotomy can be very precisely characterized from using the heavy tail large deviation formulation. So let's go. Let's look at the most the simplest example. So suppose that it's random walk. Xi's are centered IID random variables mean 0, but it's heavy tail. Then this version of large deviations hold. So if you are familiar with the light tail large deviations, you will see some similarities and differences. The similarity, the limit of the probabilities are bounded by upper and lower bounds. But here, there's no log term here, as opposed to the classical large deviations principle. And the rate function is not there. Actually, it's here. In other words, roughly speaking, this is what it means. So this probability, so remember that A is something that a set, for example, this is the set of paths that tip below 0, so bankruptcy scenarios. So this is a rare event, and as the scaling primary goes infinity, this will go to 0. How fast? It's determined by this number. So this plays the role of rate function in classical large deviation principle framework. And remember that alpha was the index of the power law. In fact, this is the index of the regular variation. I'm just showing this as a power law just because of this different simplicity. But the point is that what's important is J of A. And in fact, we're going to cover it through. So this will be this formulation, heavy tail formulation of large deviations will be the subject of tomorrow's lecture. And one consequence of this exact asymptotics as opposed to log asymptotics is that you actually get the conditional, the convergence of the conditional distribution in very precisely in weak convergences. So the conditional distribution of the process given the rare event converges to some random object that has jumps jump with sizes bounded from below. So this is a very, very precise characterization of the catastrophe principle. So which is this? Okay, so again, this okay. So one thing that let me emphasize. So we are going to be so the so these types of asymptotics applies to a very general class of A. But exactly what class of A we're going to be precise tomorrow. But for very general set A, which are in the path space. So because of this, it applies to a wide variety of problems. So for example, this is what we have started with. This is random walk version of the Rhee problem that we started with. Whether the path crosses certain level at some point. And this is light-tailed, what light-tailed LDP predicts. This is what heavy-tailed LDP large deviations predict. And if there are jumps, if you put a constraint on the jump sizes, then you may need multiple jumps. And in case you're interested in the events that process hits below a certain level and end up above certain level, then these are heavy-tailed, light-tailed, and heavy-tailed scenarios. And again, you see that none of the this is not flat. So because this is mean zero random random walk, this is a nominal path. So you expect like nominal behavior is being flat, but you see that here it's not flat anywhere. On the other hand, here this is flat everywhere, but there are just two very strange points far from the nominal behavior. So again, conspiracy and catastrophe principle. And you can even think about this complicated case. So the rare event is that the path stays between the curve, two curves. So again, this is a nominal case, but in the light tail case, it's a tight string solution. In heavy tail cases, this is what how this rare event happens. It's just normal everywhere, but there are just a few strange points. All right, so it actually also applies to much more complicated examples. So for example, we can analyze the congestion probability of queuing systems, multiple server queues and queuing systems. And this is probably more of interest to OR people here rather than machine learning people. But the point is that it applies to a wide variety of problems because of the sample path large deviation formulation. And so many rare events of your interest can be written in this way, and the sample path large deviations allow you to analyze the ETA rate of such rare events. Okay, so these were so I've been working on these types of characterization, like characterization of the catastrophe principle in different stochastic processes. But then the point is that whenever you have heavy tail processes, especially regularly varying, the rare events can be characterized by the minimal number of jumps that you have to add to the nominal path. So here, I'm going to be a little bit more precise tomorrow. In fact, the minimal number of jumps is not exactly the correct characterization. You actually have to consider the cost. So each time you make jumps, you can think of paying a certain amount of, let's say, a certain amount of money. And this amount of money depends on the index of the regular variation. So if you have positive and negative jumps with different regular variation index, then alpha and beta, let's say, and when you make this jump to this side, you pay alpha dollar. When you make jumps to this side, then you pay beta dollars. And you're actually minimizing the cost rather than the number of jumps. So that so I'll be precise tomorrow, but let me just work with proxy, the minimum number of jumps in when you have only single regular variation index. All right, so this is another example where having this large deviation formalism helps to resolve some old open problem. So this is about a rare event simulation, and I may be able to. I'm not gonna go into the detail, but let me just quickly give you some idea of how this can be helpful. So suppose that you have a coin and you want to know the probability of head-in conflict. The easiest way to have rough estimate is to flip the coin multiple times, count the number of head, divide by the number of flips. So 100 times, you're gonna get pretty reasonable estimate. It's probably somewhere between 40 and like 0.4 and 0.6. But suppose that you're interested in the probability that it lands on its edge, not head, not tail, on edge. So this will be some small probability. It's going to depend on which coin you're going to be using. The European coins may have higher probability, but especially UK. But let's suppose that the probability is 1/1,000,000, let's say. Then it's most likely to be 0 if you flip the coin 100 times. Right? So you have to report 0, and then this is probably a reasonable answer in the sense that it is close to the right answer is close to 0. But is that what you really want? Probably not, because what you want is how close to 0 is it? If you're investigating the probability of nuclear meltdown, you don't want to say it's 0, right? It's useless. So you want to have some sense of whether it's 1/1,000,000, like it's 1/1 once every 200 year event, once every 1,000 year event, or once every year event. So if the probability is 10 to the -6, then you'd like to see to get a reasonable estimate, you have to flip the coin, let's say a few million times, because you want to see this happening a few times at least. So now computing the probability of compared to the computing the probability of head, computing the probability of edge becomes much more expensive, computationally expensive task. And so of course you can just keep simulating until you see these rare events happening. But some popular ways to address this challenge is so-called importance sampling. The idea is to construct an alternate universe. So if the problem is the rare events, if events are the probability is small, then let's construct a universe where this is not small. This does not have small probability. Then perform the experiments there and then recover the probability using the relationship between the alternate universe and the current universe. And so what do I mean by alternative universe is importance sampling distribution, another probability distribution, and you generate the indicator random variables, and you compute the ratio between p, the nominal p, and the alternate distribution q, and then you report the weighted sum instead of just fraction. So in this context, coming back to this context, what I mean by this is just same events. So if the rare event has happened, then it's 1, if not 0. Again, this is weighted sum. So the key here is that you're going to get unbiased estimator here, but the choice of good alternate universe is crucial. If you choose Q to be Q in a wrong way, then you actually end up with infinite variance, something even worse than what you started with, and it can also be very misleading. So the two rule of thumb for designing good alternate universe are these. So you want to pick Qn, the alternate universe, as close to the conditional distribution as possible. And you also want to bound ratio, likelihood ratio. So this is where the knowledge of the rare event, the large deviations come into play. So you wanna be able to bound this, and you wanna be able to design something that's close to this. And this requires some analytic understanding of the system. So now I'm gonna skip the details here, but let me show you some numerical results. So this is actually about the reinsurance example that I've shown at the beginning. So these are scaling parameters. So as the scaling parameter increases, it's going to be rarer and rarer. So you would expect that it will be the relative error will increase, but with the right choice of this alternate universe, we can actually control these relative error in such a way that it's bounded. So the problem in sense becomes more challenging, but the number of simulation runs required stays the same. And compared to the naive Monte Carlo, so I changed the axis to the log scale, and then this is how it compares to the naive Monte Carlo. So the y-axis is log scale. It's orders of magnitude more efficient. Right. So this is just an example that I wanted to show you as a consequence of the large deviations formulation that we have, heavy tail large deviation formulation.
Sorry, could you go back and explain again the difference? So which one is the importance sampling, or like?
Oh, these are importance sampling estimators, and these are naive Monte Carlo estimators. So the relative error is orders of magnitude larger with live problem.
And what is the beta here? What was the beta?
Oh, so beta, these are indices of the regular variation.
I see. Okay, thank you.
Sure, thanks. All right, so another short digression. So heavy-tailed Weibull distributions are something that's in between regular variation and like really light-tailed distributions. So you expect some intermediate behavior between heavy and light tails. It's still heavy tail, but it shows some interesting intermediate behavior. So I may touch on this topic maybe on Friday if I have time, but let me skip this. All right, so now finally back to the stochastic gradient descent. So this is gradient descent, deterministic gradient descent. This is where you are. You move to the opposite direction of the gradient, but you move only this much. So this is called, this is step size, but often in machine learning context is called learning rate. So in many cases, the exact gradient is not available. So it's replaced with stochastic, like unbiased estimation of the deterministic gradient. So conceptually, you can decompose the stochastic gradient with true gradient and the noise. And obviously, this W depends on the choice of eta. So let's make the dependence clear by indicating it. And then it's convenient to think of it in the continuous time space. So let's write this same thing in the continuous time. If you do so, then this W eta converges to a deterministic process, which is a solution of this differential equation. So this is called gradient flow. The limit is called gradient flow. And so here's so as the scaling parameter, the learning rate goes to 0. It converges to the deterministic limit. So this is actually law of large numbers, and this is how it looks like with the scaling parameter pretty large. So 1/5. So this is a 90-degree rotation of the lost landscape or objective function that looks like this. So this is the objective function, and the true like if it's gradient descent, then it's gonna slide down to the local minimum. But because of the stochasticity, it can actually behave somewhat differently. But as the scaling parameter becomes smaller and smaller, it converges to a deterministic limit. By the way, if you have any question, please feel free to interrupt. Okay, so this is the solution of the differential equation. But of course, depending on where you have started, there are many different possibilities. So if you started from here, it's going to follow this path here, and so forth. But if you start on this side, then you will always end up at the local minimum associated with this side. And if you start from the other side, then you're going to end up at the other local minimum. So you can think of this as one attraction field associated with this local minimum, and this as another attraction field associated with this local minimum. So this can also be confirmed using simulation experiment. So as the scaling parameter goes to 0, you see that the paths look like it determines the gradient flow. So again, this the behavior, especially rare events, can be characterized by large deviation. And if you remember what I've shown in the previous, like in the earlier part of this talk, this may look familiar. So again, J is the number of jumps that characterize the rate of decay. And in fact, this is a number of jumps that you have to add to the nominal path. So nominal path was flat zero function, or this function with slope, the straight line with slope. But here, the nominal path is actually the gradient flow. So what do I mean by adding jumps to the gradient flow? So this is what I mean. So you follow the gradient descent, gradient flow, and jump. And then when you land on here, and then you follow the gradient flow that corresponds to the point where you land. So this is adding another jump, which is. So these are the gradient flows with added jumps. And again, J of A, the number of jumps that you have to add, characterize the rare events. So let's see how we can analyze the probability of escaping from attraction. One local minimum to another one. So how many jumps are required? You need at least one jump, of course, otherwise you're gonna end up there. But if this jump is large enough so that you land on the other side of the attraction field, then that's enough. You're gonna end up here. So J of A is equal to 1 here. And you can confirm this using the simulation result again. So again, here what I've done is I generated path. I've only collected the ones that actually the SGD ended up moving to another attraction field. So as the scaling parameter increases, you see some pattern here. So in the light tail case, SGD climbs up the hill, fights the gradient, and then moves to the next attraction field. In the heavy tail cases, it follows the gradient flow, and all of a sudden there's a single big jump that drives SGD to the other attraction field. So it becomes a little bit more clear when you see when you consider gradient clipping. So this was the stochastic gradient descent. You apply this truncation operator. So what is phi? You keep the direction, but you make it c, make it shorter if it's greater than, if the size is greater than c. So each step size, you apply this truncation operator. Then it turns out that W eta still converges to the gradient flow W. So the same limit, same nominal path, but see how the rare event changes. So in this case, suppose that the radius of the attraction field is larger than the truncation threshold, but less than twice of the truncation threshold. That means in one step you cannot escape, but with 2 steps you can escape, 2 jumps. So J of A in this case is equal to 2. And if the radius is between 2 times of the threshold and 3 times threshold, then J of A will be 3, because 3 jumps will be required, and that will be enough.
So
And
you don't know the threshold in practice, right?
that's right. So threshold is what you choose when you're running the algorithm. What you don't know in practice is the radius R.
Oh, sure. Yeah.
The Ross landscape is million or billion dimensional, so it's not an easy.
And that's another question. Like your recursion is one-dimensional or multi-dimensional?
So so it can be multi-dimensional. Yeah. So I'm going to show some one-dimensional result, but some portion of it we have multi-dimensional result. Some portion of it we one. Okay, so this can be also confirmed with simulation experiments. Again, the same conditional distribution on the variable. So now the heavy light tail pattern didn't change. It still climbs up the hill and moves to the other direction. But in heavy tail case, there are always two jumps, and outside of that, it always follows the gradient descent. So it always toward the local minimum. Okay. So again, these are conspiracy and catastrophe principle. All right. So this is large deviations of SGD, and this actually leads to the analysis of the global dynamics of SGDs. So turns out that you can actually this is a building block that you can use to analyze the exit time and also the path of the whole sample path of the stochastic process, like scaled SGD. So this is what we had, but it turns out. So this was very useful, for example, when we were analyzing the queuing systems and designing simulation algorithms. But it turns out that you need a little bit more than this, and you need a uniform version of this. So here I have some uniform like infimum and supremum here, where x is the starting point, and and it's local in the sense that A here is something that shrinks to an atom. So that if you take the limit, then you still have these upper and lower bounds. So one of the key tools that we have we found useful in establishing the heavy-tailed large deviations was so-called M convergence, and it turns out that for this version of it, we need the uniform version of M convergence. So here, okay, so yeah, so those will be. I'm gonna explain what exactly those are in Thursdays on Thursday. But here's some trailer. So this is M convergence. This is an generalization of the weak convergence and also regular variation. What we need is something like this. So with this, we can actually establish that locally uniform version of large deviation, and that which paves the way to the exit time analysis. And so because the M convergence is in one sense a generalization of weak convergence, there's a Portman theorem, and the uniform version of M convergence also has Portman theorem, and but it's a little bit, it's not as clean as the weak convergence or even M convergence, non-uniform M convergence, but we can do it, and it turns out to be useful. So this, again, this slide, I'm not asking you to parse everything here, but the point here is that this condition is more or less same as the large deviations, and this can be also derived from the large deviations. What this means is that you're not going to be staying. So if you are in the attraction field, you will either hit the minimum or escape the attraction field. You cannot stay there without hitting minimum or leaving too long. So this also can be derived from the large deviations, and this condition also means that you are supposed to hit the atom. So you are expected to hit the atom soon. So all of these actually are implications of large deviations, and this is a condition that we. So this is a condition that we. So we define the asymptotic atom as something that satisfies these conditions. And if we do have asymptotic atom, we can actually lift the large deviations to exit time analysis. So this is a precise statement of the exit time analysis. But again, I'm not gonna ask you to parse this. But one implication is this. So this is exit time. The first time it exits from the current attraction field. Lambda is scaling parameter. So if after scaling, it converges to exponential distribution. So what this means is that this is reciprocal of this, like in terms of scale. So it's the exit time scales in this way. So remember that eta is the learning rate, so it's some small number. So 1 over eta is large number, and it increases according to this power. And 1 is 1, alpha is the index of the regular variation, and L here is the ratio between the radius and the flipping threshold. So this is exactly how many times you have to make jumps to escape from this local attraction field. So yeah, so this is based on this limit theorem for the exit time and exit location. In fact, because you have the exit limit in terms of the exit location, which I'm going to make precise later this week, you actually have convergence, sample path convergence. Sample path convergence of the scaled SGD. So if you scale the time of your SGD, then it converges to a simpler process, Markov jump process. Continuous time Markov chain with discrete state space. And what's peculiar about this limit is that the state space of that Markov chain consists of the local minima will associate with the widest attraction fields. So sharp local minima are completely eliminated from the path of the limit process. Therefore, you get this ergodic type result. So you measure the amount of time you are near sharp local minima, divide by the total amount of time. So this is a fraction of time you are around sharp local minimum or sharp local minima. It goes to 0. So what this means is that you wait for long enough time as until this ascendance kicks in. Then you don't have to monitor anything. You just wait and stop at an arbitrary point. You're almost guaranteed to be around wide local minimum. Okay, so I'm a little bit over time, but let me wrap up in a few minutes. So going back to the old picture that we have started with, so now this picture probably has become clear. So in the heavy tail cases, you are able to explore all 4, and the sharp ones go away if you apply gradient. This shows the scaling of the exit time. So it shows that it does scale as expected. And this shows the path of the scale process. So it does indeed look like a Markov jump process. Here it jumps more often. But indeed, the limits look like Markov jump processes. So you can also confirm the same thing in 2-dimensional space. But how are we gonna define the attraction field and confirm this in million or billion dimensional actual deep learning loss landscape? So we can't. So instead, what we have done is to test a new training strategy, which involves both inflating tails and truncating at forward. So this sounds somewhat contradicting because you are injecting heavy tails and then you are shaving it. But as we have seen, that's actually how you are supposed to do. just adding heavy tails doesn't work. Just truncating doesn't work. You need both. So here's how we have done it. So the typical way you get stochastic gradient is a small batch SGD. So this is stochastic gradient. But what we do is we add noise. In particular, mean zero noise, because we are subtracting large batches. One stochastic gradient with from another stochastic gradient. So the mean cancel out. They are both unbiased, so mean cancel out, and you are left with some noise. In particular, if you use large batch here and small batch here, then this is a proxy of the deterministic gradient descent. So this is something that's close to the pure stochastic gradient noise. Now you multiply by heavy tail random variable, parallel random variable, some pretty heavy tail. Then this becomes heavy tail stochastic gradient. No matter what, no matter whether you have heavy tail or not in your original stochastic gradient. So again, we do apply truncation at forward, although it sounds a little bit strange. Then this is what you get. So here we present two different choices of two different variations. So those are depending on whether you use the same thing here or use independent copies of this. But the result is more or less the same. They are pretty much the same. In any case, the performance on the test set improves. And in fact, we can also confirm that the sharpness of the solution that we find using SGD also becomes tempered, so it's less sharp.
70% of what exactly? Sorry.
Oh, so these are like so for image like benchmark image classification text. Like how often you are right about like whether it's dark or cat is.
Okay.
All right, so you can. So this is extra experiment with slightly more involved architecture and in combination with like batch normalization and learning rate scheduling. But the point here that I would like to make is that this is a benchmark. This is what a usual small batch gradient descent is. So large batch is not supposed to work well, indeed. But this is when you only this is when you only add heavy tails without clipping. And you see that gradient clipping with light-tailed noise doesn't do anything because SGD never tries to make large steps. Adding only heavy tails actually messes up training. So you actually cannot train, even you cannot optimize the training, even the training error. So especially if you look at this, we tried hard to actually train it, but we couldn't. So you see that both truncation and injection of heavy tails are crucial here. And also, one thing that I didn't mention is that we have fabricated or we have generated heavy-tailed mean zero noise using actual data. So conceptually, in principle, you can also use just normal 0, 1 or 0i and just multiply by regularly varying one-dimensional random variable. This actually doesn't work. So the direction of the noise does matter. Okay. So so we have been working with a company called Moloko, which is one of the leading mobile ad companies that So there has been some delays because of this because of the IP and so the contract issues, and then also some of the sorry, but anyway, so yeah, there's been some pause, but we're resuming, and we're going to see some results. I mean, so the point that I want to make here is that sometimes so there are many different variations of GDs. Sometimes you specifically promote flatness as opposed to sharpness, like avoid sharpness in some optimization mechanism. But in many contexts, in real life neural networks, you actually cannot afford very complicated algorithms. And even when, so either you use some distributed systems, or you can use TPU, which simplifies conceptually a lot. But then sometimes it may be difficult to use even small batch gradient descent. So the point I'm trying to make here is that in many cases, you actually want something conceptually simple, easy to implement. And our algorithm, although it was highly counterintuitive, because you have to inject heavy tails and then shave it. But once you understand the theory, the algorithm itself is conceptually simple. So in cases you actually have those constraints, this is something that you may want to try. All right, so we have seen some catastrophe principles, and I mentioned briefly that that goes for the new heavy-tailed large deviation formulation. Eric and I have established has led to some solution to some of the problems. But for the metastability analysis, like the global dynamics analysis with global dynamics, we need actually a little bit different formulation, slightly strengthened formulation. And this actually reveals the global dynamics of the SGD and allows you to have some control over its dynamics, like limit behavior, such a way that you can actually achieve certain amount of improvement in the test performance in actual deep learning tests. All right, so again, this is the plan for the rest of the week. Thank you very much.
Questions? So how do you explain that the standard norm when you, instead of taking the large batch minus a small batch, if you replace something, it will not work?
So it's actually well-known phenomena. So the shape of the noise matters. So we don't really know exactly why this happens, but so there are like many interesting peculiarities in the landscape of the deep learning. So loss landscape of deep neural networks, and so yeah, I don't have very clear explanation of why this is the case, but then in which way you escape from the local minimum seems to matter. So yeah, I may be able to discuss this a little bit toward the end of this week, but there is this phenomenon called edge of stability, and it suggests that there's some very strange structure in the loss landscape of deep neural network that promotes the behavior of SGD in a very particular way. So yeah, I don't really know how to explain this, but the phenomenon itself that the shape of the noise does matter. Therefore, the direction that with which you escape your local absorption does matter.
So maybe I misunderstood your recursion. So you want using a one-dimensional normal. So that's what.
No. Million dimensional.
Also just but symmetric one.
Right.
Or just a symmetrical kind, that's what you use.
But does it get worse with higher dimensions? In 3 dimensions, it's better if you do the normal than if you do it in the million dimension.
So, okay, so,
You see what I mean?
yeah, so let me show you, yeah, let's go back to this example. So, so here, no matter, like even, so some of the new things, new phenomena emerge as you start to look at higher dimensions,
Yes.
especially deep
Yes.
learning
Yes.
landscape. Because here, even untruncated heavy tails are good enough, right? So it does promote flat local minimum. One caveat here is that this is not exactly representative. Like this is nothing to do with deep learning landscape. Especially the reason why it's more concentrated here is because this is wider than this. So if you actually have something like this, then the total mass around these will be larger than here. In this case, but in this case, still this will be dominate. This will dominate, and these will go over. So there's it's slightly this picture is slightly misleading, and so I'm also gonna mention this later this week, but in this one-dimensional case, you can actually come up with an example where there is some directionality, so that you are actually like the this one may not actually end up finding a flat local minima, but even in two-dimensional case, it changes quite a bit. And then in million dimension, I don't really know, but my speculation is that pretty much all the attraction fields are connected, like basically adjacent to each other, so that the direction of the noise starts to matter a lot. And then also those kind of pathological cases actually probably wouldn't arise that much. So that's I skipped the speculation, but
Sorry,
Yeah.
2 questions. First, does it matter that the guide that you use in your rescaling have to do with a large batch? So couldn't you have taken 2 small
yeah. So
small
actually,
batch? Reading?
if you use small bits, it still works. The 2 small batches, subtract 2 small bits, somehow it still works. So seems that the direction does matter, but there is probably some symmetry in some because just subtracting 2 small bits.
And does this direction matter problem or phenomenon? Do you think it's related to the fact that it's over-parameterized?
Probably. I think everything about a deep neural network has to do with overparameter. But by the way, not any deep learning like deep neural network works, right? So you need like there are some particular architectures that work better, and that seems to have to do with some regularity of the loss landscape. So for certain DNN architectures, the loss landscape is highly irregular, almost impossible to optimize. But with certain like popular ones, seems to have much nicer.
For the large deviation result, the only property of the loss landscape you're using is just the width of the. Is it the only parameter used in the result?
So
Or do you need more?
so the large deviation, there's no width that comes into play. The exit time analysis,
Yeah.
yes, right. So
That's the only.
yeah, so the height, so the height will matter in terms of the exact probability, but only height tiny amount because asymptotics doesn't change with the height. So if you increase the height, there will be no difference in terms of asymptotics. And and the reason is because it's almost always driven by jumps. The escape is driven by jumps.
This truncation eliminates sharp local minima. What about if the global minima is sharp? Does it also eliminate? It doesn't find it.
Also, the one peculiarity here is that so in the loss landscape of the deep neural network, seem to be. Think of this strange property. It's almost always like pretty much all the local minima are global minima.
Yeah.
So you can almost always achieve near zero training error. So pretty much everything is global. Yeah. Did I answer your question?
More or less.
Okay, well we can chat.
Okay, so there are no more questions, I think. So,